and welcome back to another episode of Statistics 479 Time Series Analysis. Now we're starting the real part of the course. We're about halfway there, and we're finally going to be doing something great. It's called Statistics, specifically estimation with time series. So for our first lecture on estimation for time series, we're going to be looking at the AR process, the classic autoregressive process. It has a bunch of phi's in it. How in the world are we going to estimate all of those phi's? Well, we're going to find out now in this lecture.
And welcome back to another lecture of Statistics 479 Time Series Analysis. Today we will be continuing on with the notes and starting Chapter 3. Chapter 3 is on estimation and forecasting. So far, we've talked a lot about the properties of different time series, the ARMA process, the AR, the MA. We've even discussed very briefly the idea of an ARMA model, where we include differencing. Now, what we're going to do is we're actually going to figure out what the parameters are in the model, because this is statistics, right? And in statistics, we want to estimate things. And what we're going to estimate are the phi's. We're going to estimate the thetas in the ARMA process. But to get there, we're going to have to take some time and work our way up to it. Today, we're going to start with just the autoregressive process, which is going to be enough work just to get through that. And then we'll start talking about how to estimate parameters for more general ARMA processes after that. So let's get into the notes and see what it's all about. All right, so again, what we're aiming for here is the idea of estimation. So the goal is, we'll say, given an ARMA PQ model, process XT, we want to estimate, well, let me write down what XT is first before I tell you what we're estimating. XT, of course, it's going to be our usual ARMA process, which I will not write like that, which I will write as WT, white noise, plus the AR piece, which is I from 1 to P of X, and I keep getting ahead of myself, phi I X T minus I, plus the MA piece, which is going to be J from 1 to Q of theta J, or not X, W T J, T minus J to be precise. Okay, so again, what we have is we have the ARP piece and we have the MAQ piece. And what our goal is to basically estimate phi hat 1 through phi hat P and theta hat 1 through theta hat P. So much like we do in, well, just about all areas of statistical modeling, we have a parametric model now. We have P plus Q, that's supposed to be a Q, P plus Q different parameters that we need to estimate. So then the question is, how do we do that? Well, unlike, say, linear regression, where you do your least squares estimator, you get out a nice answer, in this case, there are different ways to do it. And if you've been experimenting at home with some of the estimation functions in R, specifically the ARMA function and the AR function, where the AR just estimates autoregressive models and the ARMA will fit an ARMA model to your data, you might notice that the answer you get out is slightly different in each case. And it's because they use different ways to estimate the parameters in these models. So we're going to start with the AR process, because, again, that's going to be complicated enough just for the beginning. And our goal will be to estimate, well, effectively, I'm not going to write it again. We want to estimate the phi 1 through phi p. We put the hat on to say that they're going to be an estimator. So there are, well, we're going to consider two approaches. There are actually more, but two is going to be enough for us for right now. We'll take the two most standard, or at least perhaps the most standard, or at least the most interpretable methods based on your past knowledge of statistics. So the two approaches that we will consider are going to be the Yule-Walker equations and the maximum likelihood, the MLE, or maximum likelihood estimator. If you recall back from linear regression class, what we would have learned is that when you do a least squares estimation in linear regression and you do a maximum likelihood assuming normal errors, you get the same answer. You get the ordinary least squares estimator. In this case, things are going to be slightly different, but let's see what happens. Don't take my word for it. Let's jump in and see what we get. So step one is, well, looking at the mean. So we'll say step one is estimate the mean. Okay, that's easy. That's X bar. We talked about that back in like day one of this class. It's 1 over capital T. I should emphasize here, just for precision, if it's going to let me do it. There we are. So just to be clear, we're assuming that we have observations x1 through x capital T, where capital T, right, is just some finite amount. So again, unlike when we're dealing with these processes as general stochastic processes, in this case, we're working with the fact that we have a fixed and finite amount of data that we'll be working with. So everything's a little bit rougher in that sense. We don't have an infinite past, which, interestingly enough, will come back to affect what's going to happen in this. Anyway, X bar is pretty simple. We sum up all our data points and we divide by the total. Okay, we've done that before. We talked about it in the first lecture. So the point of pointing it out is to say, thus, we can instead work with the series xt minus x bar, or just assume that the mean is 0 of xt. So the point, like we've done a lot in this course, is let's just assume the mean is 0 because it's going to make our lives a lot easier. And if it's not 0, well, we estimate it and we subtract it, and now it is 0. So, oh, okay, good. We can do that. So then the question is, where do we go from there? Well, before we jump in and try to estimate those parameters phi hat, we should probably try to estimate the variance. Let's say estimate the variance sigma squared of the white noise process WT. Right, WT is white noise process. It's going to have mean 0. It's going to have variance sigma squared. And, well, we want to know what the variance is. And if you run one of these functions in R, it's probably going to calculate a variance. So then how does it do that? Well, let's look at that. So to figure that out, what we're going to do is we're going to start with the idea of saying, well, xt is going to be, let's just write it out. It's WT plus phi 1 xt minus 1 plus sum all the way down to phi p x t minus p. All right, that's just our autoregressive model. Now what we're going to do is we're going to multiply. Actually, no, sorry, we're not going to multiply yet. We're going to compute the covariance of each side, right? This is equal, I guess the variance. All right. I'm being imprecise here. What we're doing is we multiply both sides by xt, and we take an expectation outside of that. So what does that mean? Well, that means that on the the left-hand side of the equation, we're just computing the variance of xt, and on the right-hand side here, we're going to have the covariance between xt minus 1 and xt summed all the way up to phi p times the covariance of xt minus p xt. Well, we can rewrite this in terms of the autocovariance function k evaluated at 0, and then we have wt plus, I'll just write it all out. We could use the sigma notation, but let's just write it like this, which is k at lag 1 summed all the way up to p phi p, k, the autocovariant at lag p. Okay, so then the thought is, well, if the right-hand side is basically, I forgot one other thing. I forgot to do it for the, I forgot to do it for our poor little white noise guy here, WT. So what I should have put in for WT here is the covariance between WT and XT. Well, in that case, by using this equation above for what XT is, at time t, it only really depends on, it is WT at time t, and then it depends on the x's at t minus 1 and so on. So using some of the properties, we find out that this is in fact just sigma squared, because it's effectively, let me write that in here, the covariance between WT and and WT. There we go. Okay, so can we do anything with that? Well, we can rearrange the equation a bit, and we find out that the variance of the white noise, sigma squared, is going to be what? It's going to be the autocovariance at lag 0 minus the sum, let's say I from 1 to p of phi I times the autocovariant at lag I. All right, so does that help us at all? Well, it kind of does, because what it means is that, well, if we want to estimate, we'll put some green hats on everything. If I want to estimate the variance, that is sigma squared, well, I can estimate all of the autocovariances. So now what I'm saying is that I can determine sigma squared. Then an estimator, sigma squared hat, is going to be a linear combination of the estimators of the autocovariances k0 hat all the way up to kp hat. But there's one problem. We don't know what the linear combination is, because these guys here are still unknown. So like I said, so far, we need to make sure that when we're estimating something, we're estimating it based on known quantities or functions of the data that we're given. We can't estimate something if it has a bunch of unknown parameters in it. So we have to figure out what the phi's are in order to figure out what sigma squared is, or sigma squared hat is. So then the next step is, let's try to estimate the phi's. So I guess the point is, therefore, find phi hats to find sigma hat squared. All right, cool. So then, well, how do we do that? Well, what we could try is to do the same thing we did up here, but instead of multiplying by xt, we could multiply by xt minus 1 and see what happens. So what we're going to do is we're going to say I guess we never really finished step 2. We got sidetracked because step 2 said estimate the variance, but oh no, we didn't quite finish that. But step 3 is going to be estimate the phi's. So if we take that equation up above, but instead we write the expected value of xt minus 1 times xt is equal to, let's say, the expected value of xt minus 1 times wt plus, again, phi 1, xt minus 1 plus phi p xt minus p. All right, so we have that. Well, what does this become? The left-hand side is the autocovariance at lag 1. The right-hand side, well, what happens? Well, first of all, the wt just becomes 0 here because it's uncorrelated with xt minus 1 because, again, it's at time t. Xt minus 1, we're assuming causal linear process so that this is equal to 0. I'm going to write that in the, I will put it over here in the margin. Note, we assume xt is causal ARP. As noted in the previous lecture, there is for any causal ARP process, there will be an equivalent, stochastically equivalent non-causal ARP process. I think it should still be the same order, ARP. But regardless, there will be a non-causal, it should be ARP, of course it would be. There will be an equivalent non-causal ARP process and vice versa. So when we're trying to estimate, we're going to just work under the assumption that we have to pick one of them to estimate. So let's estimate the causal one because we live in a causal universe to the best of our knowledge, I guess. So far, the future has yet to dictate the past, at least to the best that I know of, whereas the past seems to dictate the future in the world that we live in. So what we will do is we will always assume that what we are estimating is going to be a causal ARP process. Now, the other interesting thing, side tangent, is that if you didn't have an ARP, if you had an MAQ or an ARMA PQ process, but you try to just fit an AR process to it without any MA piece, you can still do that. But certain weird things will happen. We'll look at that later, but just keep that in mind. That right now we're assuming that what we have is what we're looking for, what we're trying to estimate is what actually is there. That is, we picked the correct model. But in a priori, we wouldn't know that we have an ARP process besides maybe taking a good guess and looking at things like the ACF and the PACF plot. Anyway, that was a big tangent. Getting back to what we were actually doing is we were trying to compute the expectation of the right-hand side of this equation. The first term is just 0. The next term is going to be phi 1. Well, it's going to be the expected value of xt minus 1 times xt minus 1. That's the autocovariance at lag 0. Then continuing on, we find that we would have, I'm going to write the next term in here. We're going to have the autocovariance at lag 1. And then we're going to sum all the way up to phi p times the autocovariance at lag p minus 1. Okay, so that's kind of interesting. We haven't quite figured out what we're doing yet, but we have another equation. Think Yule-Walker equation. We have another equation here that is in terms of phi's and autocovariances. Let's try it again. And this time we're going to do the same thing, but if we multiply by, I'm going to continue to skip more steps with each time I do this. If we instead try multiplying by xt minus 2 and doing the exact same thing we did before, then what we're going to get is an autocovariance at lag 2 on the left-hand side. On the right-hand side, we're going to get a 0 for the white noise, but we aren't going to get a 0 for the xt minus 1. We're going to get a phi 1 autocovariance at lag 1. Then we're going to get an autocovariance at lag 0. And then we're going to sum all the way up to phi p times the autocovariance at lag p minus 2. So you're noticing kind of a pattern here. There's kind of a diagonal pattern thing going on. I guess we'll just do that. So what happens if we push ourselves all the way to t minus p? So let's do this all the way down to multiplying by xt minus p on each side of this equation. Then what we end up with is an xk at lag p, right? Because t and t minus p are p time points apart. And when we jump onto the right-hand side here, we're going to get a kx at lag p minus 1. We're going to get a kx, oh, I put k0 there, a kx at lag p minus 2. And this will continue up to phi p, which will be a kx at lag, I think 0, right? Double checking, yeah, 1, 2, yep, 0. Just making sure it's not 1. Sometimes it's like, is it 1 or is it 0? No, in this case, it's 0. Okay. So now we have a whole bunch of equations. It's a system of linear equations, and we can solve that. So let's look at that. All right, so let's recap. What we have is a system of p linear equations with p unknowns, which is phi 1 through phi p. So we solve it with linear algebra, our good friend that is sort of everywhere in statistics. All right, so let's think about how we can write this out in a better way. What we can do is we can write, so what I'll say is we write k, capital K, is going to be gamma times phi, where capital K is the vector of autocovariances from lag 1 to lag p. And I like to write that this is in RP, just so I always remember where we're working. We have a p-dimensional vector of autocovariances from 1 to p. All right, the next thing we get is we get our gamma matrix. So gamma, actually, let's do phi first. It's easier. Gamma's big. So phi is going to be our vector of unknowns. That's just going to be phi 1 through phi p. And then we have gamma, the big matrix. And gamma is going to be, I guess, again, this is in our p dimensions. And then we're going to have a p by p matrix, which is going to have the autocovariance at lag 0, at lag 1, over here at lag 1, on the main diagonal at lag 0. And what we're going to do is this is going to continue all the way down the matrix. Down at the bottom here, we're going to have, I think, p minus 1. Let me, double check. Yeah, p minus 1. And kx at p minus 2, and so on. And then over in the corner, we're still going to have a kx at 0 on the main diagonal. And yeah, if we really wanted, I can write kx p minus 1 up here in the corner. So we have a giant matrix, which is coming from all of the autocovariances that exist within this system of equations. So now, well, what do? Well, what we do is we solve this. And what we can say is that, therefore, we estimate kx at lag 0 up to kx at lag p, and compute sigma hat, or not sigma, phi hat to be, what is it? It's going to be gamma hat inverse times k hat, where the hat just means that I'm estimating all of the elements within that matrix gamma and within the vector k. Right. So now we have a way of doing this because we know how to compute the autocovariances, and what we found out is that our, basically, let's change the color. Basically, what we showed here is that our phi's hats are just linear combinations of autocovariances. Excellent. Remember when I said this whole course is basically just autocovariances, autocorrelations, and so on. Mainly, it's like the only thing we really do. And what we found here is that we can just take a big matrix of autocovariances, a vector of autocovariances, multiply the two together. We'll inverse gamma first. Inverse gamma, multiply it by 2k hat, and we get out phi hat, an estimator. And this is the Yule-Walker equations. This system is the Yule-Walker equations. All right, that's actually pretty cool. I always found that kind of neat. But we're not quite done yet. Where are we going to go next? Well, the first thing is we never finished step 2. We never actually finished estimating the variance sigma squared of the white noise process. So now we can finish step 2 above, which is to say that we can now estimate phi hat squared by k hat x at lag 0 minus, I guess we can say, the vector phi hat transpose, it's just the dot product, times k hat. Right, because if we go back up to where we were in step 2, way up here, what we said is that we have two things to consider. We have k hat at lag 0, and then we have a linear combination of the k hats at lags 1 to p. So that's basically just what we're doing down here. Cool, so now we can really just estimate everything. We have that, and we have that. And of course we have x bar as the mean, but that's super boring, so we'll just not worry about that because we don't have to, we already did it. In fact, we can actually also write this as k hat x at lag 0 minus, because if we look at the definition of phi hat above, we can write it as a quadratic form now as k hat transpose gamma hat inverse it's symmetric, so I don't need to transpose it. Yeah, technically it would be gamma hat inverse transpose, but gamma hat symmetric, its inverse is symmetric. Therefore, I don't need to transpose it and have terrible notation, because inverse transpose and transpose inverse just looks terrible on paper and stuff like that. So we'll avoid it. So we can actually write this as a quadratic form. And thus we are, we're good with that. So then the question is, does this estimator make sense? We often in statistics want to know properties about the estimator that we have. Is it, does it converge, for example, to the right thing as the data size gets bigger? You want to think the answer is yes, because intuitively, we know that it's based on the autocovariances, and as the data size gets large, the estimator of the autocovariances converges on the true autocovariance. So hypothetically, if that's converging, you would want to think that the phi hats would also converge in the sense that the better estimate we have for autocovariances, the better estimate we'll have for phi hat. But we can actually write down a theorem which will formalize this a bit, and I don't think I want to actually prove it. We'll see if we have time or if we actually want to go through it. I'm pretty sure it's in the back of the textbook where I was using to organize this class. So in the notes, it's theorem 3.11, and it's the asymptotic normality. Normality for YW being Yule-Walker. And basically given phi hat and sigma hat squared as above for a causal ARP process, then what we have is that the square root of t, it's always square root of the sample size, right? At least in parametric stats, times phi hat minus phi will converge in distribution to a normal random variable with mean 0 and covariance matrix. This is a vector, remember, it's not a sigma squared times gamma inverse. And we get convergence in probability for sigma hat squared to sigma. This is convergent probability. And this is both as capital T goes to infinity. So what does that mean? Well, that means that for large T, phi hat looks to be multivariate normal or Gaussian. So that's quite nice. It's not it's not like an independent or in anything, because we're going to have this gamma hat inverse, which most likely will not be diagonal unless and that would only be the case if then of course it would almost never be diagonal, right? Because gamma hat or gamma, the matrix here, would only be diagonal if all of the autocovariances are 0 up to lag p, which means we have something that looks uncorrelated, at least up to lag p minus 1, like some type of white noise process. So that would be really boring. So basically, you have a vector, but you have a normal distribution, but you have a non-diagonal covariance matrix, meaning that the estimates, the phi hats, have some dependencies between them. So it is good to be aware of that these are not independent estimators. There will be some dependencies between the phi hats. Oh yes, and we get a corollary from this. Corollary. And the corollary is that basically the PACF is also asymptotically normal. Remember in the last lecture, the last one, when we looked at the PACF function for the AR1 process, we saw that the PACF for the AR1 at lag 1 will have a value that is effectively what phi 1 is, or it's an estimator. So in that case, we have that the estimated phi hat is also the PACF. Now for larger P ARP processes, we do not have that nice kind of like correspondence, but there's still a very close relation between the PACF and the phi hats and everything. And what we have, again, we're not going to prove it now, but just so you know, the idea is that I'll say with the same setup as above, we have that root t times the estimated, this is squiggly or I guess script phi at lag h, will go converge in distribution to a normal 0, 1 random variable for h greater than p, which means that, again, if the lag is greater than the order of the autoregressive process, then it means that the PACF should look, after rescaling by the sample size, should look like a normal random variable. And hence, we can use that fact to look at a PACF plot and determine whether or not the value is big based on comparing it to the normal distribution, assuming that the sample size t is large enough. So that's a nice extra bonus that we get, a little bit more of a formality than what I was doing in the last lecture, where I was just kind of writing stuff down and saying, okay, the PACF, the true phi, basically the last lecture, what did we do in the last lecture? We said in the last lecture that phi no hat at lag h will equal 0 if h is greater than p. So now we've kind of strengthened that to the idea that the estimator phi hat will have like a central limit theorem going on. It'll look like a normal random variable for large values of t. So just learning more about the PACF function as we go forward. All right, so I have some examples of how this will work, but we're not going to do that right now. What we will do is we will jump into the idea of maximum likelihood estimation, and then we will revisit all of this in R code. So the next idea is maximum likelihood estimation. All right, so then how do we start an MLE problem? Well, we want to maximize the likelihood. We need the likelihood. What's the likelihood going to come from? It's going to come from a distribution, in this case, the normal distribution. So for this section here, we assume that WT is Gaussian white noise, because we want a distribution to work with. If it's not Gaussian white noise, we're going to get a different likelihood, and it means we're going to have to, well, work a lot harder. It's already kind of annoying with the Gaussian distribution. Let's not go outside the Gaussian distribution in this course, but it is worth noting that up above for the Yule-Walker equation, we didn't make any distributional assumption. All we said was that we have uncorrelated white noise so that we could write down all of the Yule-Walker equations. If it's not uncorrelated, well, all bets are off. So we definitely need that. In this case, we're going to strengthen it a bit for maximum likelihood estimation, assuming that our white noise is Gaussian. It's a pretty good assumption because it happens a lot of the time. But you could have some heavy-tailed noise or other issues, or other types that you might have to worry about. And because this is, well, super annoying to do, we're going to once again start with the AR1 process, because it's a lot easier for me to actually write down and it's not going to be as much of a headache. So what we're going to do is we're going to write down xt is going to be mu, the mean that I like to ignore, but this time we're going to write it down, times phi x t minus 1 minus mu. It's kind of a weird way to write it, yes, plus wt. The idea is that if xt has mean mu and it's stationary, then xt minus 1 also has mean mu. Therefore, this piece in the parentheses is a mean zero process. So what we have is white noise mean zero, thing in parentheses mean zero. Mu is just mu, so it's not a random variable, but it could be any real valued. Mu can just be some real number. So now what we need to do is we need to write the likelihood, but we don't want to just write down the likelihood. Well, we want to write down the joint likelihood of the entire data. So we want the joint likelihood, which is going to be L of mu, phi, and sigma squared, right? These are the three unknown parameters in our model: the mean, the phi parameter, the autoregressive parameter phi, and the variance of the Gaussian white noise process, sigma squared. And we're going to condition that on the entire, I guess I use semicolon, so we'll use semicolon, the entire data set x1 up to xt. Okay. Now, if we were to just use the definition of likelihood, we know that this is just the joint probability density function with x1 through xt given the parameters mu, phi, and sigma squared. So again, this is likelihood. This is the joint probability density. All right, well, it's Gaussian, right? Because if Wt is a Gaussian white noise process, then any of these derived processes from Wt will also be Gaussian. So f is going to look something like a normal distribution, but I have no idea what the parameters are going to be. So that is the mean and the covariance, right? For a Gaussian process, we just need to know the mean and the covariance, and we're done. But I don't know what it's going to be in terms of mu, phi, and sigma squared. So instead, what we're going to do is we're going to decompose the likelihood into a conditional, into some conditional distributions. So instead of trying to attack this joint distribution directly, what we're going to do, and I'm going to drop the conditioned on the mu, phi, and sigma squared because it's just going to make it look messier if I don't. We're going to start with just the density function for x1. Then we're going to consider the density function for x2 given x1. Then we're going to consider the density function for x3 given x1 and x2, or maybe I should write x2. Oh, that's right. Yeah, I guess. Well, I'll write it out like I'll write it out like this, and then we'll simplify that. And then we can write out xt given x capital T minus 1 all the way down to x1. But what we have is that xt is a Markov process that is order 1 AR. So because it's an order 1 autoregressive process, all of the information about time little t comes from time little t minus 1, and the rest of the past is irrelevant when it comes to conditioning. So what we can actually do is go back in here and we can drop out anything but the most recent. I shouldn't be doing x's in red because it's just going to be confusing with the fact that I have x's all throughout here. So we'll just slash it out. So we get rid of that guy. We get rid of everything in here. And what we're left with is just a big product of conditional densities. We're going to have an f of x1, and then we're going to not say equals, but we're going to multiply that. We are going to multiply that by t, little t, from 2 to big T of f of x little t conditioned on xt minus 1. So now we have a much cleaner way to write this, and we have a bunch of simpler conditional Gaussian density functions rather than one giant joint Gaussian density function. All right, so hopefully that actually helps us. Right, so what we can say is that the first thing, stop saying step 1, step 2. We'll just say the first thing we're going to note is that x1, our first guy here, is just going to have a normal distribution with mean mu and with variance term being sigma squared divided by 1 minus phi squared. Okay, why is that true? Well, the mean is just the mean. It's just mu. This is just the variance, or the autocorrelation at lag 0, covariance at lag 0 for AR1. Right, we did that already. And one subtle note, which is assuming an infinite past. So if you recall, when we actually computed this, that's where the 1 minus phi squared in the denominator is coming from, right? It's an infinite geometric series going, I guess, into the infinite past. It's a geometric series going into the infinite past. When we sum up all the terms, we get a 1 divided by 1 minus phi squared. And then the sigma squared is just floating around there when we take the, when we compute the variance of the white noise process. Okay, so we have that from before. Again, technically our data is finite, but mathematically we're assuming that this causal AR1 process can be extended into the infinite past for the sake of estimation or mathematics. Anyway, this will be what we have for x1. And then the question is, well, what in the world do we do for the rest of these things? Well, luckily, Gaussian distributions are super robust. You can kind of torture a Gaussian distribution and you still get out a Gaussian. You can add them together. You can take conditional you can do conditioning. You can do product distributions. You can do, in certain cases, you can do a lot of things and you still get Gaussian distributions out. So the claim, right, is that this xt conditioned on the previous guy, xt minus 1, is also going to be Gaussian. And in fact, if we recall that, Well, I'm going to write down the answer, and then I'm going to explain why it's the answer. So the claim is that this thing, xt conditioned on the previous observation, is also going to have a normal distribution. The mean is still going to be mu. And, oh no, it's not going to be mu, sorry. It's going to be mu plus phi times x t minus 1 minus mu. And then the variance is just going to be sigma squared. So where's that coming from? This is because we have xt is equal to wt plus phi xt minus 1 minus mu. So if I condition on xt minus 1, conditioned on xt minus 1, what do I have on the other side of the equation? Well, if I condition, I get that wt is still wt. I get the exact same thing, except that when I condition on xt minus 1, I'm treating this guy here as a constant. So we're treating this as constant. And this guy here is just normal 0 sigma squared. So all I'm saying is I have a normal 0 sigma squared distribution, and I'm shifting it by that thing, phi xt minus 1 minus mu. And hence why, when we go back up to what my claimed answer was, I have a mean, which is going to just be, oh, I forgot my extra mu in there. That's why I'm like, something's missing. We need an extra mu here. But that thing is still just constant. And then the sigma squared from the white noise is just going to be the sigma squared in the distribution here. So ultimately, I can write down what all of these all of these conditional density functions are, combine them all together, and I get the joint density function. This is a trick that is quite useful when you have anything like a Markov process that has a finite, I guess, horizon for, what's the right word? Causality, I guess. The fact that we only care about the previous time point to predict the current time point. In this case, that means that I can throw away all the complex conditioning, and I'm left with just a very nice, simple way of writing down the joint density. Again, rather than trying to attack it all at once. So then we put it all together. And what do we get? Well, we get our likelihood. I'm not going to write in terms of all the x's. Well, I'll just write it like this. Let's just write it out. I have a lot of room on my page. I can just keep creating more room, so we'll fight our way through it. Anyway, what is this going to be? It's going to be a big equation. It's going to be the it's going to be the variance. It's going to be 1 over the square root of 2 pi times the variance. So what we're going to get is we're going to get out front, we're going to get something that looks like, I guess I can just take the square root of the whole thing. So what we're going to get is we're going to have a 1 minus phi squared. That's coming from 0.1 up here. The density function for x1. Now, when we move to the denominator, we're going to get a 2 pi, and we're going to get a sigma squared, and we get one of these for all of the terms in that product, which is right there now at the top of the screen. There are t terms in the product, so we get t of them. But if you recall what the density function for the Gaussian is, we get a big square root over this whole thing. Maybe I should write out the side margin, right? Normal mu sigma squared has a density function that's going to look like 1 over the square root of 2 pi sigma squared e to the, we'll say exp, minus, I guess I need a argument, well, what are we doing? We'll say t, I guess. We want to, yeah, we'll say x minus mu squared divided by sigma squared. Right, that's my univariate Gaussian density function, right? It's always hard to make sure I get all these correct. Oh, there's a 2. I knew there was something I was missing. We're divided by 2 sigma squared. Okay, now I feel better. I felt like there was something wrong there. Okay. So this square root bit is just out front. Then we're going to have a big exponential. So what is up in the exponent? Well, a couple things. First of all, we're going to get the magic 1 minus 1 divided by 2 sigma squared. That's usually there. But there's a lot more to go. So we have our minus 1 over 2 sigma squared, and we're going to have a big summation in here. Well, what do we get? For the first term, which is just f of x1, right? That has a mean of mu. So, and a variance that also includes 1 minus phi squared. So what we end up with is something that looks like x1 minus mu squared times 1 minus phi squared. That's going to be this bit over here. I take my x, I subtract the mean, I square it, I divide by the variance. The sigma squared is in all terms, so we're just going to leave that in front of this giant curly bracket. But the 1 minus phi squared only applies to the first term here. It's only in the variance for x1. It is not in the variance for xt conditioned on xt minus 1. So that's why that's there. And then we're going to sum up all the rest of the terms. Again, we're in an exponent, so the nice thing about that is that our product becomes a sum. And we're going to sum t from 2 to capital T. And then we need a couple things. We need xt minus the mean, mu, and we're going to subtract from that. Basically what we're doing is we're doing xt minus its mean. Its mean is here, but the way I'm going to write it is I'm going to take the first mu and attach it to xt, and the second mu is already attached to xt minus 1. And this whole thing is squared. And we end the curly bracket, and we end the giant square bracket, and we have this grand joint density function. Like I said, I wouldn't want to have to write this down from scratch without first using this conditioning approach. Okay, so what do we do with this thing? We want to find the maximum likelihood estimator. And if you recall from, say, linear regression, the thing in the exponent is actually the sum of squares that we want to minimize, right? The e to the something, it's an e to a big sum of squared terms. We want to minimize that. So what we can do is we can consider that this thing here is a sum of squares. So minimize it. Right? Question mark. Well, kind of. Let's look a little bit more at this. So what we're going to do first is write down the exact same thing I had in the in the exponent here, and we're going to denote that as S. Let's make sure we got this right. S sub u. And this is going to be the unconditional sum of squares. So the hint is that if I call this the unconditional sum of squares, there's probably going to be a conditional sum of squares coming around. The unconditional sum of squares in terms of parameters mu, the mean, and phi, the autoregressive parameter, is going to be, well, it's exactly what I have there, but I will rewrite it just to make sure it's exactly clear what's going on here. The squares on the inside there. And then we sum t from 2 to capital T of x t minus mu, the centered process. Again, this is why it's kind of nice to not just assume that mu is 0, but here we actually want to estimate mu, so we're going to bring it in everywhere. X t minus 1 minus mu squared. Okay, so this is our, and let me write out under here, we'll say this is the unconditional sum of squares. All right, so what do we do with this? Well, let's see what we can happen if we, well, I guess we got a couple more things we have to do. Another thing we need to do is consider the log likelihood and use that to get sigma squared, because in our unconditional sum of squares, we have mu and we have phi. We don't have sigma squared. To get an equation for sigma squared, what we're going to do, so this is the first thing we're going to look at. We need that defined. The next thing we're going to define is the, well, not define. The next thing we're going to do is we're going to take a partial derivative of the log likelihood with respect to, I'm not going to write out likelihood of whatever, it's the log likelihood with respect to sigma squared. Okay, so that's, what's that going to be? Well, let's write it all down and see what happens. So what do we have here? Well, the first thing we're going to have is we're going to have a lot of terms that don't actually matter. Going to this square root bit over here, the first thing we're going to get from the numerator is a 1/2 log 1 minus phi squared. That's the numerator bit. The denominator bit is going to be a minus t over 2 log, I guess we'll break it into two pieces. The one we don't care about, which is the 2 pi, and the one we do care about, which is log of sigma squared. That's going to be the one of the important pieces. And then the last bit is we take a log of the exponent, and what happens? Well, what we end up with here is just, I guess, minus, because there's a minus sign in front of everything. This is just the what's in the exponent, the unconditional sum of squares, mu phi, divided by 2 sigma squared. Okay, so I'm going to take the derivative of each of these terms. Luckily, 2 of them just vanish. This one gone, this one gone, and we're left with, well, 2 things. We're left with the derivative of the log of sigma squared, which is going to be t divided by minus t, divided by 2 sigma squared. Then we're going to take the derivative over here, and we're going to get a plus su, unconditional sum of squares, mu, not sigma phi. And into the denominator, when we take the derivative of this, I guess what, a 2? Oh no, we're taking it with respect to sigma squared, so it's like the derivative of 1 over x, which is minus 1 over x squared, so we're going to get a 2 sigma to the 4th. All right, and then if we set this equal to 0 and solve, we get, well, simply what we get is we get that sigma hat squared, which is going to be now the MLE I want to emphasize this is different than the sigma hat earlier in the lecture. So maybe I'll just write here, this is the MLE. In this case, it's just going to be the conditional sum of square, or the unconditional, sorry, sum of squares divided by the total sample size. So again, it looks a lot like what you get when you want to estimate a variance. You get the thing in the exponent from the normal distribution divided by the sample size. And if you recall back from Calc 101, when you compute the maximum likelihood estimate for the normal univariate normal distribution, you get the sum of squares divided by the sample size. And then what we say in Stats 101 is that, well, wait a minute, we should probably divide by the sample size minus 1 to account for the fact that we estimated the, to make it an unbiased estimator, since we estimated X bar as the sample mean. But effectively, we're getting the exact same thing is happening here. It just looks a lot more complicated. But besides the complications and the nasty formula, we basically have the same thing, which is our maximum likelihood estimate is the sum of a bunch of squared things divided by t. Okay, so then the question is, how do we get, I'll say, but how do we get mu hat and phi hat? Well, it's not that easy, and there's not going to be a nice closed form in this case, sadly. So the answer is, this is a question, so we question mark it. And the answer is, well, it's not that easy, because if we basically we get mu hat and phi hat by solving a non-linear system of equations and in math, right, linear things, good, non-linear, bad, right? It's whenever you have a linear system like we did with Yule-Walker, it's great. Invert a matrix, we can do that, no problem, right? Non-linear system, it says, well, that's annoying. It means we probably aren't going to have a nice closed form. Instead, what we're going to have to do is try some numerical solver and hope that it doesn't fail miserably. I will write down the equations just so that you have them here. The equations are going to be there's going to be two equations because we have two parameters, right? We have two things we're trying to estimate, phi and mu. And if we go back to I'm skipping the step, but if we go back to our log likelihood, we take derivatives with respect to phi and mu, we get out two different equations. It's not really worth writing out all the details because it's just an exercise in calculus that's kind of boring. And we're eventually going to find a better way to estimate these in 1 second from now. But I will write them down so we can stare at these equations. And the equation is going to look something like this, assuming, because I'm actually just copying this now rather than deriving it like I did with the last thing, that hopefully what I did when I derived it the first time, I derived it correctly. I trust me, more or less. Anyway, we're going to get something that looks like this crazy equation. That's equation 1, and then equation 2, if we take the derivative and then set it equal to 0, I think in this case with respect to phi, we end up with something like minus phi, 1 minus phi squared, minus 1 over 2 sigma squared, and then 2 phi x1 minus mu squared minus 2, the sum t from 2 to capital T of x t minus phi. Yeah, time series is just the worst when it comes to equations, right? It's just equations ad nauseum. And then I think there's an x t minus 1 minus mu. So again, not the nicest thing to look at or to solve. Now, the point that I was trying to make is there are some nonlinear things to worry about. The fact is, we have a couple terms that look like, well, let's switch to red, that look like this, where we have a mu times a phi, we have a phi divided by a 1 minus phi squared. Here we have another mu times a phi. So again, it's not the easiest thing to just work with. So what we're going to need to do is come up with a better approach. And that is where the conditional sum of squares comes in. I think, yeah, this will be a little bit of a long lecture, but we'll just get through all of this, and then maybe we'll do some nice R code in the next one and take a little break from all the crazy equations. Right, so instead, we can condition on x1 to effectively remove the f of x1 from the likelihood. And this is where the problems come from. From this guy. So that's where our nonlinear problems are coming from. If we condition on the first, basically what we're doing is we're just throwing out x1, but what we do is we write a conditional likelihood. So the conditional likelihood is going to be mu phi sigma squared conditioned on x1, which is why I had to be careful I'm right semicolon in the other case, because technically there's what I'm not writing here because the notation would be terrible, is a semicolon x2 through xt, and then conditioned on x1. And what we do with that is we effectively throw out the first Gaussian bit, the f. We just take f of x1 and it's gone. Why not? It's just one data point. Who cares? And what we're left with is the same equation from above, but we don't have a couple things. The first thing to note, there is, well, I guess we have a t minus 1 over 2 here, or the square root of this whole thing. There's no 1 minus phi squared in the numerator. That's good. And then when we look in the exponent, we get the sum t from 2 to capital T. Oh, that's another typo, man. I think I wrote these last year during the first COVID lockdown, so things became a bit messy with my course notes. I will try very hard to update them. Hopefully, by the time you're watching this, or, well, by the time someone's watching this, we'll see how fast I can get to the updating. Anyway, the idea is that we still have a minus 1 over 2 sigma squared there. And then what we're going to have is an xt minus mu minus phi xt minus 1 minus mu squared. Maybe I shouldn't trust myself. No, this makes sense. What we basically did was we took this, so if we look at what that formula looks like, and we go back up to the one that just fell off the top of the screen, what's missing? Well, what we did was we got rid of the 1 minus phi squared in the numerator there, and we got rid of this term. These are the two terms that came from f of x1. They are the nonlinear pieces, because now when we go back here, we have a nice looking sum of squares without any strange issues arising. Well, yet. I'll show you what happens. So what we get here is I guess what we need to do is we need to call this thing in here SC of mu and phi, which is going to be the conditional sum of squares. Cool. And we get a new another sigma hat. So this is now the third estimator sigma hat that I'm going to have in this one lecture. Sorry about that. But I really don't want to start writing sigma tilde and sigma other crazy sigma prime and other things. It's just going to get confusing. This time we estimate it by looking at the conditional sum of squares divided by capital T, but we have to subtract 1 because we have one fewer data point. We threw out the first data point, so that one is no longer there. So now we have yet another estimator for sigma hat squared, but this one I claim is easier to actually solve. So first of all, what I'll say is we rewrite the conditional sum of squares to be the sum T from 2 to capital T of xt minus alpha plus phi xt minus 1 squared, where alpha is going to be mu 1 plus phi. So now, what is this? This is simple linear regression. Simple in the sense that it's one input, one output, not simple in the sense that it is easy by any means. Basically, this is just least squares regression, in the sense that we have something that looks like y is equal to alpha plus phi x, where y here would be xt and x would be xt minus 1, etc. And then I guess we would have like an epsilon noise term in there. But yeah, this is just a sum of squares like we would see in linear regression. So we can solve that. So now we get a matrix. We can say let X be the matrix, the design matrix, using the terminology from linear regression, where we have all ones in the first column corresponding to the intercept, and in the second column we have a bunch of x's, which are going to start from 1. Yeah, of course, because we're using 1 through t minus 1 to predict 2 through t. Yeah, so we have to do, the predictors are going to be x1, x2, x capital T minus 1. And the response variable, let's see, what notation was I using here? I didn't actually use a notation for that. I'm going to write it out like regular linear regression. The response vector y is going to be x2, x3 through xt. Again, it's like linear regression, except we're using x1 to predict x2, x2 to predict x3, x3 to predict x4, and so on, all the way up to xt minus 1 to predict xt. But if I have this, then I know what my answer is, so then therefore we can just write down the least squares estimator, and we get alpha hat, and we get phi hat, and that is just going to be everyone's favorite x transpose x inverse x transpose y, which is just going to be a big product of a bunch of points in the time series. But that's a really nice and simple thing because I have my time series x1 through xt, which means I can really quickly compute alpha hat, phi hat. And then we have that after a little bit of maneuvering, we find out that phi hat is actually can be written as a ratio of the sum t from 2 to capital T of xt minus x hat. Sorry, x bar 2. I'm going to explain this notation in a second. X bar 2 in brackets, xt minus 1 minus x bar 1 in brackets in parentheses. And in the denominator, yeah, we're dividing by that thing squared. So I will explain this in one sec once I write it all down. Okay. All right, so I have to tell you what x bar 1 and x bar 2 are. If my voice holds up for just another few minutes. X bar 1 is the mean of the data, excluding the last point. It's t minus 1 times the sum little t from 1 to t minus 1 of xt, and x bar 2 is the average of all the data excluding the first point. T from 2 to capital T, xt. So again, excludes x capital T, and this one excludes x1. And this phi, actually, you would have seen something that looks like this in linear regression class, because in linear regression class, you would find something like, oh, beta hat just happens to be the sum of x, or y, we'll say yi, xi, divided by the sum of xi squared. So that's exactly what this is. What we have here is we have xi is the predictor, it's t minus 1. Yi is the response, it's t, and we're dividing by the sum of the xi squareds in some sense. All right. Okay, so we have that. We're almost done. Let me circle this in a big green box. And then therefore, alpha hat, which is just an intermediate that we're going to use to get mu, is going to be x bar 2 minus phi hat x bar 1. And if we go back to whatever alpha was supposed to be, which is mu times 1 plus phi, we can just, well, divide by 1 plus phi, and what we get is that mu hat, our estimate for the mean, is going to be the average of the data excluding the first point minus the average of the data excluding the last point. But I forgot to multiply by phi hat. Oh, come on, OneNote. There we go. Phi hat x bar 1 divided by 1 minus phi hat. It is minus, right? Yeah, good. Okay, so we have that. This is so much better than last year. Last year, I used to get kicked out of the class all the time because I'd be talking too long, and the next class would try to come in and get in when fair enough, right? But still, now I can just keep talking as long as I want, and you can decide whether or not to tune out. But we're almost there, and we're getting to the good conclusion, which is before we're done with this lecture, I want to say let's compare Yule-Walker 2MLE. Well, the phi hat for the Yule-Walker, in this case for an AR1, right, is just going to be the ratio of the auto covariance at lag 1 to the auto covariance at lag 0. And when we write that down, we end up with something that looks like the sum T2 to capital T, xt minus x bar, x t minus 1 minus x bar. And the denominator, because this is just the estimate of the auto covariance, right? T from 1 to capital T of x minus x bar squared. Okay, so that looks pretty similar to what we wrote above, but it's not exactly the same. Above, we have an x bar with a sub 1 or a sub 2 because we're excluding a point. In the denominator, in the Yule-Walker case, we don't have that. We're just taking the entire the mean of the entire data set x bar. And similarly, in the denominator, we're summing t from 2 to t. Wait, is that? Yeah, no, of course it is 2 to t. And in the denominator here, we're summing over the entire data set t from 1 to capital T. So asymptotically, as the data set gets really big, these two estimators are the same, but for a finite set of data, and especially for a small time series set of data, you will get slight differences because of how they deal with the edges, the edge or the boundaries of our data set. Beyond the x1 and the x capital T, everything else that happens in these two methods is the same, but how they deal with the boundary condition, the fact that our data doesn't extend infinite past into the infinite future, that's where the differences occur. And that's where we have to just be aware of that. They're both very reasonable estimators, and in general, they will give you more or less the same thing. We will look at that a little bit more, but we're going to do that in the next lecture after I have a chance to rest my voice and come up with some good R examples for us to look at. We'll look at the AR. What we'll do is we will look at estimating models using the AR function, and then we'll jump back into the notes and we'll talk a little bit about forecasting, because, you know, if you have a time series process, you don't just want to know what it's doing, you want to know where it's going, right? It's a stock. I want to know, is it going up or down? Is it the climate? Do I want to know if it's going to get better or worse, right? I want to know where these time series are going. So we'll talk about forecasting in the next lecture.